Okay, right. Suppose I'm going to start with forces. So forces are simple. It's push or pull on an object. So on an object. So when you push or pull it, you exert a force. Right. That's simple. Yeah. Yes.
Amma, it's the first sentence and you're asking questions.
No, like,
Oh
are
nah.
you projecting the thing already? Because I can't see it.
Oh my bad.
What was it to be projected from there?
I said one
No,
sentence, dog.
no, like
Seriously.
whatever's coming.
How do you know there's something coming?
Sorry, please keep quiet.
Please
I
keep
think
him
you
quiet.
need to remain on mute for the rest of the lesson.
Yes, Amma. You.
Right. Now, generally, forces are simple because when you do it, when you cannot see the actual force, you see the effect. So you see the effect of a force. Now, generally, forces do the following. So it can either cause a so let's say an object is stationary. It will cause it to move slash accelerate, start moving, to start moving. Then it will cause it to stop moving, accelerate, and deaccelerate. It will cause rotation and deformation, change in direction. So that's the simple part of it. So generally we measure it in newtons. So keep that in mind. Now, when I hold a 1 kilogram weight in my hand, does anyone know how many newtons of force I'm exerting on this to hold it up?
10.
Do you know why it's 10?
No.
Okay, right. So generally it's not actually 10. It's actually 9.8 newtons. I know what the textbook says. Textbook says 10. But if you are on Earth, your gravitational acceleration is 9.8 meters per second squared. Meaning, let's say you fall from a height of 200 meters. Every 1 second, your speed, let's say your speed starts at 0, but then every 1 second per second, you gain 9.8. Then it's like 18, 19.6, so on. You keep on increasing. That's what second squared means. So it determines acceleration force. Now, generally, to calculate newtons in this case, we take our mass times by the acceleration, which gives us our newtons. So it's 1 kilogram times 9.8, which gives us 9.8. Generally, we work in kilograms for this, and this is Earth's gravity, unless it tells you otherwise. And this is your weight. Now, something about weight versus mass. Yes,
Um, the 9.8, is that is that our like the weight on Earth, like our
that's
gravitational
our
field?
gravitational acceleration on Earth.
Oh, okay. Thank you.
Right. So the difference
Wait,
between
BP.
yes,
What's the difference between gravitational force and gravitational acceleration?
they're the same thing in this context.
Ugh.
Right. So the difference between weight and mass, simple. For mass, it's the amount of matter in object. So like let's say 8 kilograms of mass, for example. Weight, on the other hand, is your mass times your acceleration. In this case, gravitational acceleration gives us your weight. Meaning, this one will stay the same. So I can be on the moon. My mass is still 8 kilograms. Let's say I am 50 kilograms. Doesn't matter where I'm going. I am still 50 kilograms. Obviously with world variation, but that's due to different factors. I can be on Earth, I can be on the moon. The amount of matter in my body does not change. Therefore, my mass stays the same. But my weight is dependent on the factor of gravity, meaning my weight changes based on gravity. Meaning weight mass is constant. Weight changes is variable, changes. Right. Now, when we look at forces, they work in pairs. No matter what you are doing, the force will work in pairs. Let's say you're driving your car. Right. You're driving your car forward. The car is moving forward at, let's say, 10 meters per second. Right. Now, you may think that, oh, no, this is only one force. But no, there's multiple forces. So we draw something called a free body diagram. Free body diagram meaning you don't have to draw the object. There's no diagram of it. It's only just a dot in the center. Right. Now you may ask what all these arrows are. These arrows represent the direction in which force is going. So if this, let's say we're on Earth, gravity is 9.8. Our, and let's say we have a mass of, so let's say our gravity is 9.8 and this car weighs 100 kilograms. You see. Right. The amount of weight pushing down, the amount of newtons is 980 newtons. And that's your F gravity. Then push it now. We're not just sinking down into the ground. There's also a force pushing us back up, which is also 980 newtons. And that's known as the F normal. Right. Now, when I'm sitting on this chair, gravity is pushing me down, but the chair is exerting a force upwards. For every reaction, there's an equal and opposite reaction. In this case, the equal 980, 980, equal, meaning the car stays planted on the ground. Now, we're moving at 10 meters per second forward. So we just put, let's just say, so in this case, you just say 100 times 10, so that's 100. Okay, and maybe write that 100, 1,000 newtons of force. Let's just say it's 1,000 newtons of force. But however, there's air resistance, so let's just say it's 10 newtons. Obviously, it's not. And that's how you draw a free body diagram. However, something to note, if the forces are equal, so these two are equal, then these lines here must be equal. But if they're not equal, this one of them will be longer and the other one will be shorter. Do we understand how to draw that? Do we understand this concept? Right. Now, moving on, this is pairs. Forces will always work in pairs, no matter what. There's always some force pushing against you. It could be less than you. Right. Unbalanced versus balanced. Must be. Right. Simple concept. When we have, because forces work in pairs, you have something known as balanced and unbalanced forces. It's in the name. Unbalanced, meaning a force is greater in one direction. So let's say you have two forces, right? And you have 10 here and 5 here, meaning they're unbalanced. This object is in motion. If the object is in motion, your forces are unbalanced because the one will be greater. Balanced forces, they equal forces, meaning not in motion. This is in motion, and that's not in motion. Right. So we're saying when the forces are balanced, when you say there's a net force, because the object is moving nowhere, it's going nowhere, it's staying still. If I, let's say I put my a box on this table and I do not move it at all. Here's my box. I do not move it at all. The forces are equal. This is both 9.8, let's just say 9.8. The forces are equal. We have a net force. Right. We say there's no net force, sorry. There's no net force in this case. But if we say, if they not balanced, when it's moving, we say there's a net force. Right. Then we get two types of, yes.
BP.
Yes. Yes, I'm listening.
So when something moves, it has a net force.
Yes.
Okay.
Because that means there's unbalanced forces. Sorry
Okay.
about that confusion. Right. Now we got two kinds of forces. There's mainly two. We look at two. Contact and non-contact. Let's see. Right. What do the two mean? Let's just read this. Right. What do the two mean, you may ask? It's in the name contact and non-contact. So let's say I push this box against the table. I have my box here, and my hand touches this here, and it exerts a force and it pushes this box this way. That's a contact force because I make physical contact. It's in the name, physical contact. Right, there's physical contact between the two objects. So, take for example friction, air resistance, compression, so on, so forth. Right, non-contact on the other hand, there's no physical contact. That means, take for example, the two objects never touch. Take for example gravity. The earth does not have to, I do not have to be standing on earth for me to exert the force. I can be inside the atmosphere and it will pull me down. That's considered non-contact. Excuse me. Think magnets. Magnets work without contact. They create attraction forces without contact. These two are not contacting, but they still pull each other. That's contact. Right. Moving on, expanding on the non-contact, we have gravity. Simple concept. What goes up must come down if your net forces are equal. Right. So let's say I throw a ball up into the air. That means the ball, when I throw the ball up, that that amount of newtons is more than the gravity at that point, meaning it goes up, 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 up. But then let's say the ball starts coming down. That means gravity is now stronger. So at some point, there's a balance in forces. One is slowly increasing. So let's say I put 100 newtons of force in it, and it goes up, but then eventually all that energy is used. It comes back down because now gravity is stronger than the force I'm forcing onto it. So it will always travel in the direction of the stronger force, no matter what. Right. Gravity is simple concept. Most of you already experience it. Any two objects exert gravity on each other. As long as an object has a mass. If an object has a mass, it exerts gravity. Gravity is based on a few factors. Weight, mass, and the distance between the objects. Right. Think of Earth. Earth's mass is so much greater than ours. So of course Earth is gonna pull us towards it. When we jump up, we will come back down to Earth, not the other way around. So mass is a big consideration. The more mass, the higher the gravity. The less mass, the less gravity. The distance between an object. If I am far away enough from Earth, gravity no longer affects me. So as the distance increases, gravity decreases. As the distance decreases, gravity increases. That's why if I'm in the deep ocean, gravity will affect me more than if I was standing here on shallow waters because I'm closer to the object. Right. Then, right. I've already gone over these conversions. I've gone over mass, difference of mass and weight. Right. I went over weight. Okay, right. Here's the formula again for weight. It's just mass times the gravitational acceleration or gravitational force, and that gives you the Fg, or which is F gravity, or mass times gravity, if you want to simplify. Right. This is the simplified formula we work with. Right. Moving on, we have magnets. Simple concept. You have two magnets next to each other, they will pull each other. Simple, simple, simple. They work with non-contact. They still non-contact forces. Now, anything that has iron, steel, we look at, so like iron, steel, cobalt, and nickel. Anything with these materials present will be magnetic, as in it will be attracted to one of these magnets. Now, simple. So, for example, we look at magnets. So it can be a magnet and one of these materials. It can be two magnets attracting each other. It can be one with a material in between. It doesn't matter. It works with a non-contact force. Right. When we look at a magnet, simple concept. We've got a north pole and we've got a south pole. The magnetic field goes from, let me just check my diagram. Okay, right. Goes from north to south. Always. These lines that I'm drawing must be parallel to each other. They never cross over. They always go from north to south. Doesn't matter. It's from north to south. Simple concept. But then that's how they attraction. So let's say I have a metal ball here. This will be attracted to the magnet, but if I have one here, it's outside of the field. It won't be attracted from towards the magnet. Right. Now we have to look at light. Opposites attract and like poles repel. Right. So when we look at this here, the field would go from north to south. Because even though they're opposite ends of the magnet with their own north and south poles, let me draw it fully for you guys. Don't forget about these fields. Okay, right. North and south poles attract each other. Opposites attract. When we put two north side magnets, they repel each other. The field goes like this here. That's why you try and push it, it repels. You do this, they attract. Simple. And the same concepts are followed here. Right. That's magnetic forces. Does everyone understand everything so far? Right. Moving on. The last one for forces. We have electrostatic. Simple. You got two objects. Let's call this object A and object B. They have protons, electrons, protons, and electrons. Everything is neutrally charged until they're not. What moves? Electron moves. They transferred. Generally, if the positive and the negative are equal, then we say it's neutral. If the positive is more and the negative is less, then it's positively charged. If the positive is less than the negative, then it's negatively charged. Right. Now, this is because of friction. Friction transfers electrons. That's all that is to it. Some transfer more, some transfer less. Simple stuff, right? Lightning, caused by static electricity. The clouds bump against each other, create friction, transfer particles. Lightning finds the closest path to the ground, which is neutrally charged. Positive, so the cloud, let's say a cloud is negatively charged. The electrons will jump from that to the ground, which is neutral. The ground is always neutral. So if this is negatively charged, then the electrons jump down there. Only if it's negatively charged. If it's positively charged, you won't get electrons jumping up from the ground. It will never work like that. It's only in one way, one direction, and only if the clouds are negatively charged. Simple, right? Lightning and safety, that's common sense. Right. That's it for forces. Does everyone understand forces? Right. Let me just go next to this one. Right. Now, electricity in systems. Now, when we look at a cell, simple. This is positive, this is negative, this is chemical, potential energy to electrical energy. Simple concept. It's a source of energy. It stores energy. Right. Quite simple concept. Now, generally we call this an electrolyte because it's a chemical solution. That conducts electricity. Right. Now, there's positive particles in here and negative particles. These are called ions. Right. When I use up, there's more negative. When I charge, there's more positive. Simple concept. Moving on. Measured in volts is the power that a battery can output. Think of volts is how hard can I push this. So let's say I have a wall here and let's call this wall this symbol. Voltage is how hard I can push through this. Current is how fast I can move through this. So this is speed, and think of this as torque. Simple concept. Voltage, how hard the push is. Current, how quick the push is. Voltage kills, not current. Voltage, if you have a higher voltage, is more generally more dangerous than a high current. Right. So when two of these cells are connected, like this here, it's called a battery, or even like this here. This is called a battery. Now there's two ways of connecting it, like this here, series and parallel. Now you may ask why the difference, parallel versus series. Starting off with series, if we do it like this here, does anyone remember what our voltage, how to calculate the voltage in a series circuit?
Since it's divided.
Current times resistance, no?
Right, so it's current times resistance, but also it's V1 plus V2 plus V3. So if this is 1.5 volt batteries and there's three of them, it's 1.5 plus 1.5 plus 1.5, and that's equal to 4.5 volts. So that's a lot more volts if we connect it like this here. So you're going to get 4.5 volts out of this, and amp stays the same. So let's just say it's 10 amps out of that battery, even though it's not. It's probably like 1 amp maybe out of this. Right. Now power, parallel. Here's the differences you're going to see now. Right. Here, okay, let me draw another one for consistency. Right. Here it's quite simple. Simple. Right. The voltage is the same. So the voltage is still 1.5 volts. The amperage The amperage will only go however fast the circuit needs. If the circuit needs 9 amps, it's going to draw 9 amps from here, whether it can supply it or not. So the amperage increases in this case. But because the circuit only demands the amperage it needs, the electrons will only flow at the speed of the circuit. So it won't go quicker or else it generates too much heat. So the circuit determines that. In this case, because the amperage increases, the capacity increases as well. For example, your phone battery might use combinations of this to get your, I don't know, like maybe 12 volts or whatever voltage your battery is for increased capacity and increased voltage. Parallel if you want more battery capacity, your batteries last longer this way. Series if you want more voltage, your batteries get more voltage through your circuit this way. Simple. Right. Moving on, resistance. Simple concept. Oh yes, voltage is also known as potential difference because it's the difference in the electrons in 2 points in a circuit. Resistance. Any material has resistance to it. Doesn't matter, it can be the highest quality copper, can be the lowest quality plastic, it will have resistance. Because as the electrons move through here, they are limited by materials. Even if it's a conductor does it well. Insulator, not so much. But a conductor will still have a small, like a zero, not even a percentage resistance, while an insulator is like quite high. So you see more drop like this here. Now, as long as current is flowing through here, there's resistance through here. And how do we calculate resistance? It's your voltage divided by your current. Simple formula. Right. Now, um, so if the material is dependent on that, some can allow electrons to flow through it easily, some don't. That's what determines its resistance of the material. Now, we look at the component known as the resistor, the infamous resistor. However you would like to draw it. If you want to draw it like this, sure. If you want to draw it like this, sure. Yes. Okay. Right. You want to draw it like this, sure. The resistor. What it does, slows down current. Current specifically, keep that in mind. And it creates heat. Heat as off product. So we use it in stoves. The element in those old stoves looks like this. This gets red hot because of the heat. So current does not flow through your well, but it's forced to flow through here. So it creates heat. Right. Resistance dependent on four things: the type of material. Let me put this here. Right. The type of material. Do you have a piece of plastic or do you have the greatest quality copper you can get? Do you the length of the wire? Logically speaking, because there's more distance to travel, there's more resistance. Number three, the thickness. Think of a highway. If you have a 1 lane highway, it's going to get traffic very quickly. If you have a 4 lane, maybe 5 lane highway, it's better flowing. The cars move much quicker there. So a thicker material is better. Number four, the temp. The temperature affects it. Hotter the conductor is, the worse it gets. That's why we generally want to keep things cool, because when we look at this here, the electrons, when they flow through here, there's a small, the heat, let's say there's a flame here, decreases that conductivity because now there's heat energy also going through here. So this moves slower now. Right. Those four factors. Longer wire, worse. Shorter wire, better. Thicker wire, good. Thinner wire, bad. Type of material. Copper, good. Plastic, bad. Temperature, lower temperatures, better. Moving on. Series and parallel circuits. Series and parallel circuits. Series circuits, simple. They one after another. They follow in a straight line. One path. Parallels, there's multiple paths. Two or more paths. Now, advantages, disadvantages. Series. Series allows for finer control. Oh, no, no, no. Let me rephrase this further. Series circuits allow for example, a switch to be placed here and to cut off the motor that's connected here from power. So generally less materials used, so it's therefore cheaper. Parallel allows for better, and we call this redundance. Redundance. Basically, let's look at your light system. Let's say you have 4 lights here, one at each intersection here. If one of them dies, does not affect any other one. If you look at your room and switch off the, let's say one light bulb dies, the others will still work because it's wired in parallel. Right. Measure it with an ammeter. Right. Measure it with an ammeter. Right. So voltage, anything when we measure anything, it's across 2 points in a circuit. It can be resistance, amperage, voltage, across 2 points in a circuit. Right? Voltage, voltmeter, simple stuff. Right, when we connect a voltmeter, it must always be connected to something in parallel. Do we know why? No, you don't have to know why. Just know it is like that. That's the way it is. Because voltage is the same across parallel lines. Therefore, it's fine. And you never feed a voltmeter directly because the full amperage will be going through there, which is very bad. Right. Simple. Must always connect it in the correct polarity, or else it will not work, or it will go in negatives. Then we have resistor again. Part 2 resistor. Got part 2 of the resistor. Right. There's something called an adjustable resistor or a rheostat potentiometer, known by different names, basically the same thing. Contains resistive material, and based on where you adjust it, different resistance. Simple. Right. Connect. No matter how many bulbs you connect in let me simplify all of these practicals. Connect more bulbs in series, they get dimmer, dimmer, dimmer until you can't provide enough current. Connected in parallel, they will all look the same and shine at maximum brightness but use the most current. Simple stuff. Right. Do you guys want me to go over all the calculations again? You know those voltage calculations for series versus parallel ammeter. Do I need to go over that?
Isn't it the same formulas as the Ohm's law, like V
Yeah, so
equals?
you know all those formulas where V1 plus V2 plus V3 in these parallel circuits equal V total, and like the resistance formulas.
Yeah.
You know those ones. Not
But
the V over I one. Not
oh,
those ones.
nah. I don't know those ones.
The more advanced ones for series and parallel circuits. That's just
Yeah.
the general Ohm's law. Do you not know these ones? Let me write it down for you. Simple. This is series parallel. Right. Parallel. Right. Series symbol. Voltage T is equal to V1 plus V2 plus V3, so on and so forth. Amp um, I total is equal to I1 plus I2 plus I3. No. That's wrong. That is wrong. Sorry. Right. This is just I1 equal to I2 equal to I3. Current stays the same. Resistance total, you're just adding up the resistors. Simple. Current stays the same in the circuit. Right. Yes, I am right. Right. Parallel V total is equal to V1 is equal to V2, stays the same. The I total is I1 plus I2 plus I3. Each branch gets a split current, each branch gets full voltage. Each component gets split voltage, each component gets full amperage in a series compared to a parallel. Right, resistance total. Now this is that long formula. You know which one I'm talking about. That's right. It's 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. That one, so forth.
Is it always gonna be like 1?
Yes, it's over. Your numerator will always be 1 in this case. And
Okay.
then you know that thing where you have to do like, you just put this in your calculator. Yeah,
Okay.
right. Right. That's calculation, series and parallel circuits done with. I did, you know Ohm's, basic Ohm's law by now. You should know that by now. Right. Your current is directly proportional to the potential difference across a conductor at constant temperature, meaning the current, when the current increases, the voltage increases. When the current decreases, the voltage decreases. Simple concept, provided that the temp is the same. Right. Safety with electricity. We have a fuse versus a circuit breaker. Simple concept. Fuse, thin wire. Too much current goes, nope, kills the circuit. Circuit breaker. You try, let's say a plug draws too much current. It switches off. Which one's more expensive? The circuit breaker. But it can be reused over and over and over again. A fuse, on the other hand, every time you break it, you need to replace it. So it's cheap. Earth leakage. Right. Let's say you pull too much current. The earth leakage will trip first, kill all power through your circuit, and that sends all the current into the ground, all the excess current. That's why it's called earth leakage. When you look at a plug, there's 3 points. 3 points, yeah. 1, 2, 3. This is your earth, this is your live, and this is your ground. Generally, this is green, this is green, this is blue, and this is brown. I don't have a brown, but this is brown. Right. So this one, yeah, if anything trips, sends all the current through it. Household wiring. Your house is wired in parallel. There's the mains and the meter box. The meter box, that's where you pay for it, like prepaid, whatnot. Mains, that's your distribution board. Underneath, it goes underground and comes into your house. Simple. That's the way you can flick it on and off. Then contains all the circuit breakers, whatnot. Right. That goes throughout your house. So they wire in parallel. So if one trips, it's fine. 3-pin plug I just explained. Live is, let's say, your 230 volts. Ground is your negative, and earth is your earth leakage. Okay, sometimes this is yellow, but most of the time it is green. Right, unlawful connections you know about. Moving on. Right, energy and in the national network. Simple stuff. Do I need to go over this stuff? Because it's literally just common sense in this case.
Nah, you don't have to.
Okay, so I'm skipping this whole section. Cost of electricity power do you need me to do? Right, let me do that then. Power is the energy used over the time, over a certain period of time. So let's say I use 100 watts of power over 10 seconds. That's 20 joules of power per second. Right, simple concept. Look at it like this, right? That's the simple power formula. Then you get the second power formula. This is how you calculate those final calculations. So your power, let's say you want to calculate the cost of how much you are paying for electricity. It's simple. So let's say pay for. Let's say you want to calculate how much you're paying for. It's the watts divided by 1,000 to get kilowatts times the price times the number of days times the time that you use it for. So using a simple example, let's say I have my computer here. It was 60 watts. So 60 watts divided by 1,000 watts. The price of electricity, let's say 3 rand to simplify things. I use it every day. So let's say 30 days. Time I use it for 5 hours. Yes. He has to tell us the price per unit. If not, you say 3 rand. Generally, you will give us an updated figure. So obviously using simple math, 0.06. Let me just make sure this. All you have to do from here is put it in your calculator. So it's 6 divided by 100, so 0.06 times 3 times 30 times 5. Obviously, you must make sure, doesn't matter in which order your formula is in because it's multiplication. So it's 0.06 times 3 times 30 times 5 is 27. 27 rand a month per month to use this appliance. That's how you calculate that. Right. This right. Watts divided by 1,000 is equal to kilowatts. You don't need to know this. Kilowatt hours. It's the amount of energy used in an hour times how many hours you're using times how many days you're using it for times the price of electricity. Simple. Generally your geyser uses most of your energy, so it's generally most of the time good to have a solar geyser because it cuts costs there. Right. Moving on, the term Forster. I am skipping mining. Good night, then. Right. I'm skipping mining in this case. And instead, I'm gonna move to the earth. Because mining you'll be fine. Right, atmosphere. We're on page 267, if anyone was wondering. Let me just find where I am quickly. Okay, let's zoom in here. Right, the atmosphere is 78% nitrogen. It's only 21% oxygen, and the others are so small percentages. So generally, we only look at the nitrogen. So what is your is nitrogen is commonly found in this form, oxygen commonly found in this form, O2, and other gases. So this is 78%. This is 21%. The other, and then there's the other gases. This is like methane, carbon dioxide, neon, ozone, xenon, krypton, so on. Right.
Sorry, BP. What's this for?
The atmosphere on page 267.
6-7. Sorry. My bad.
Nice calm. Right. So as we go up, remember how I said earlier that gravity is affected by distance. Pressure is determined by gravity in this case. So as we are closer, so let's say Earth is here and here's the atmosphere. The further we get from the atmosphere, I mean from Earth, the less dense oxygen and other gases are. Do you know why? Because pressure compresses gases. Gases can be compressed. The compressed gases are denser, have more particles inside them. Excuse me. So generally, you get a layer where it's the most dense, which is about 16 kilometers for your information. Right. So it serves, what is the function? Serves as oxygen, obviously. Right. But pure oxygen is deadly. So we need nitrogen because nitrogen dilutes the oxygen. So it protects Earth from the ultraviolet radiation, ultraviolet coming from the sun. It's radiation you cannot see, but is present there. But the atmosphere doesn't allow it in. Blocks a lot of ultraviolet. Reduces temperature variation. It traps heat by just being there, oxygen particles. It reflects it back onto Earth. Simple stuff. Right. Structure of the atmosphere. Got the troposphere. You got the mesosphere. The oh, sorry, I did this in the wrong order. Let me start again there. Right. Troposphere, stratosphere, stratosphere. Ignore the spelling here. The mesosphere and the thermosphere. Right. Simple. This is the thinnest one. This is going upwards. This is the thinnest one. However, spelling. Right. This is the smallest. And yet it contains 70% of our 70% of gases because of how as we go up less dense. Right. This is where everything happens. Generally Mount Everest is like 10, so it's around 10 kilometers tall, which is around slightly Mount Everest is slightly lower. Right. Now as we go up the temperature decrease. Now let me show you how finished this is. So we got layer 1, layer 2, layer 3 and layer 4. As we go up in layer 1, so here's the up, and here's the temperature. It's decreasing, so it starts at -50 and it goes to 50 degrees. So let's say we start here. As we go up in altitude, that goes down. So higher up we go in layer 1, the colder it gets. Then in layer 2, the higher we go, the hotter it gets. Layer 3, so it's a zigzag line. 2 and 4, it's the inverse. 3, it goes is the same as 1. That's simple. Right. Now what are the functions? They perform different functions, these guys. Right. What do? They regulate temperature, so on and so forth. Troposphere generally contains 70% of all gas particles. Keeps the gradient determined with altitude, so on. Okay, weather. Weather is only happening here at the bottom, the troposphere. Weather happens here. There's clouds here. Right. Then every living thing lives inside here. No bird will go higher than this. Stratosphere. Simple thing. Contains something. Then we got the stratosphere. Stratosphere. Simple. Think ozone. Ozone is a gas also, and it's a layer. It's about like it's very thin, very very thin, and it blocks UV light found here in the stratosphere. Right. Um. That's what the stratosphere is about. It has this layer in it. The mesosphere. Meso. Mesosphere. Simple. Has It's thin and cold. Right. Meteors come in here. The rocks, the space rocks, but whatever they are. Generally, they burn up in this layer. They burn up in this layer. This is where you get shooting stars. This is where you get shooting stars in the mesosphere. Right. Moves at it's very quick. So generally, this is where it becomes too hot and burns up. Right. So if it's too small, it just burns up. If it's big enough, we may get like a small portion of it or not. Right. Simple. Then the thermosphere. Simple. This being the least dense. This is where stuff happens. After this layer, it's gone. There's no more atmosphere. This is where it ends. Right. Um. So it's very cold, but however, because it's so high up, the temperature is not consistent at all. It can reach 1,500 degrees, but it can be very cold. Right. That's that. Now, simple thing. Greenhouse gases trap heat back in Earth, increasing temperatures, creating global warming. Generally, it's methane, carbon dioxide, sulfur dioxide, etc., etc. Even water vapor is a greenhouse gas. The greenhouse effect traps heat. The worse this gets, the hotter it gets. The hotter it gets, the more climate change, and so on and so forth. You know that. If you don't know the effects, just go and Google it and you'll get that. And that brings us to the end of the lesson. Does everyone understand everything I've gone over? There any other topics you would like me to go over?
Wait, Pravir, will we have to know the birth and death of a star?
No, that's not on either breakdown.
Oh, okay. So, thank you. Yo, PP the code. Yo.
We almost done here. Just 5 more papers for you guys.
Writing robotics and thing and arts is so unnecessary guys. I can't hold you. Yo, long day.
Yeah, I'm gonna be here if anyone needs any other question. I don't know if the recording will upload in time because it's